Hi everyone, welcome to AI Talk hosted by E2E Networks. My name is Aarti Sharma and I take care of business development for Maharashtra region. The purpose of hosting webinar is to build an AI community wherein the members can benefit from the industry experts. And today we have Mr. Ramjee, who is a founder and CEO at dblue. Today he will talk about machine learning lifecycle management. And further he will put his insight. So if you have any queries, you can raise your question in Q&A section. Once Ramjee is done with his talk, he will answer all your queries. Now I request Mr. Ramjee to take it forward from here. Thank you so much.
Hi everyone, good evening. This is Ramjee here. Give me a second, I'll just share my screen. Hi, you are able to see my screen? Marty, maybe you can prompt.
Yeah.
Yes.
Yeah.
Good evening, I am Ramjee here. I am founder of dblue. I'm an engineer by profession with over a decade of experience at various startups, scaling the products and technology at them, notably Just Eat, which was into food ordering. It got acquired by Foodpanda, and then subsequently at Big Decisions, which was a news corp company. Over the last decade, I've built a lot of engineering systems and have used machine learning in the products that we built. And what we currently do is a culmination of a lot of learnings from those days. I'm also a no sugar advocate, and you can find me on Twitter at Ganti. Yeah, so when we say machine learning lifecycle, a lot of people have different definitions so that we all have a common ground. Let's look at how we, see this machine learning lifecycle, right? It refers to an iterative process that spans cross-functional teams which define, build, deploy, monitor, operate, and improve ML systems. The keywords that we should look at are cross-functional teams, apart from the rest of the other various activities that we just defined. We'll come back to this thing as we go forward in our talk. So typical perception a lot of people have when they think of machine learning, and which is rightly so, because there has been a lot of proliferation in the media and our surroundings around machine learning and AI. So people think that when we talk about machine learning systems, it's only algorithms that one has to create. I wish that was so, but the actual reality is this. Most of the times, if you have to operationalize or productionize a machine learning system, you would probably look at only about 15-20% of your effort in uh, out of the total effort, right? So a lot of effort is actually spent in the surrounding auxiliary systems to make this machine learning algorithms serviceable, right? Some of them being, you talk about data collection, then you have feature extraction, you have data validation. We'll touch upon some of these terms as we go. You have the various analysis tools, process management, the serving infrastructure itself, and monitoring, etc. Right? So let's see how uh, the machine learning systems are a bit different from software systems in their complexity. Many of you probably are familiar with software. If not, I'll give a brief about the complexities involved in the software, and then we look at how these complexities are different in machine learning systems, right? A typical machine learning system life cycle, if you look at, has it's very iterative in nature, and you look at you start with defining your tasks, and when you define the task, one of the important things which also needs to be considered is where the data comes from, right? And when I say define task, you are basically trying to look at what is the kind of problem that you are trying to solve using machine learning. uh, if you don't have data, or if your data is very deterministic, then you can probably get away with writing rule-based systems, which you don't necessarily call them as machine learning systems, right? So that's one of the reason why it's very important to look at data around when you're considering what is the problem that you are trying to solve. The next step, again, very neglected but very important, is one should consider not just whatever data is collected, but how the data is collected also. We all probably heard of the cliche, which is data garbage in is garbage out, and that very much stands for the machine learning systems too. If you don't have good data, then the system cannot do anything about it. It will churn out garbage predictions. So it's very essential that you have good data, and having good data starts with thinking about how you collect good data. So that's where it starts. Then you have various other steps, like model exploration. So most of the model development, in this particular phase, it's encapsulated in this phase, the training and development phase. And once you have your models ready, then you basically test and evaluate before you put them in production. Subsequent to testing and evaluation, once you put these models in production, again the deployment in production is not as straightforward as in software systems. We will touch upon this particular aspect too as we go. Uh, Once you deploy the models, you have to continuously monitor them. And here we are not just talking about monitoring from availability itself, right? So in typical software paradigm, we when we talk about monitoring, we typically look at the health of the system, whether it's servicing all your requests or not, and whether it is doing what it is expected to do. But in machine learning systems, monitoring also uh, takes a very different definition, and it has a very different set of requirements that you one looks at, right? Now, before we proceed and talk about all the various stages that I just mentioned, let me first go to and describe the various uh, actors involved in a typical machine learning when you have to productionize a machine learning system, right? We all are aware of data engineers, data scientists, and ML engineers. Uh, but so that we are all on the same page, let me just describe how I define each of these, right? Your data engineers are engineers who are responsible for data collection. Partially, most of it might lie outside of their domain, but they are the ones who are responsible for getting data from various sources, from various silos in the organization, or from different sources like over different APIs and all. Clean it up, do the processing, and make it ready for the data scientists to or researchers, right, to consume them. Now, the researchers or data scientists, these are the people who actually develop your models. They create, or they write the code in various frameworks, like be it PyTorch, be it Keras, be it TensorFlow, or any of the other many available frameworks. They are the ones who code up the various models, and then build them, train them, and finally take the call whether a particular model is up to the mark in terms of whether it can go for deployment or not. Once the data scientists or researchers, they hand over these models to the ML engineers, these are the people who are responsible for productionizing, right, and deployment. So sometimes these productionization may mean just making the model available at a particular location, and in other cases, it may involve a lot of engineering. Right? We'll go through each of these as we go forward. Now, the challenge here is, as we have already seen, there are three different roles. There are also other auxiliary roles which don't come in the direct path, but very, very important for product managers of QA. Now, all these multiple people are involved, and in companies which are of reasonable size, these are large teams in their own, which essentially means it all leads to a lot of friction between the teams. Excuse me. Uh, because each of the teams have their own priorities and their own goals. Unless all these teams are working on the same common goals, you really have a tough organization at your hand, right? So people issues, given that all these are cross-functional and in many cases they don't share common artifacts or common understanding, it becomes much more difficult and challenging to make sure that all of them lie on the same page. Now, in this talk, we'll not be looking at how to solve these people issues. We'll primarily be interested in the technology aspects of Lifecycle. So, if you compare from a typical software to machine learning systems and what is different, you can see this on the screen, right? We have code, which is common in the software systems. But in machine learning, we have two more variables here, which is model and data. So all the changes happen on these three different axes compared to only one axis of code on in a software systems, right? Now, what this actually means is, even if your code does not change even a single letter, like even if you have not removed a semicolon or an extra space or anything like that, right? Your output will change because over a period, models disintegrate, right? I mean, they decay, and you need to ensure that you train your models and keep them up to date on a regular basis, right? Now, now, typical problems in software systems that we see are dependency management, reproducibility, testing, and monitoring. All the machine learning systems also go through and face the same issues. Now, in addition to that, there are a few issues that are very, very specific to ML systems, right? These are like these increase the complexity much more. Some of them being, it's very hard to predict the output of a model. If you kind of want to look at a small subset of the thing, the output of models is hard to predict. They are very hard to test. They are hard to explain and hard to improve. So let's say you have a particular accuracy, and then on a given data set you have hit a particular accuracy that your team is happy with. Now, to improve on that is a harder thing. Similarly, hard to predict the behavior. You have trained these models on a particular set of data. Now, the distribution of data might be very different. So the distribution of data in your training might be very, very different from distribution of data in production. Or even if with smaller variations, assume that you have about 5 to 10% variation uh, of data in the data distribution in production, which basically means your system will infer or predict wrong in all those cases, and you don't even know how badly the predictions might be. So it's very hard to predict how the systems work. Similarly, for the same mentioned reasons, because it's very hard for us to get a good distribution of data. Now, it's also very hard to test. And the moment we talk about models which are dependent, and what do I mean by that, where one output of one model goes as an input to another model, we are talking about two indeterministic systems which are much harder to test. And most of us are familiar in this space that it's hard. Like, the output might be within what you are expecting uh, of a given model, but it's it's next to impossible to explain why the model actually predicted or gave a particular output, right? So these are some of the additional complexities that machine learning systems have, which our typical software systems don't. Now, another thing which many people don't consider when they are talking about machine learning systems, given that there are so many frameworks and so many ready-made algorithms which are available outside in the open source world and even in the closed source world, a lot of people actually think it's very uh, easy to build machine learning systems, and that's actually the case. If you have to build the ML systems, that's very fast and cheap. In fact, you just need to probably have the right kind of data for you to solve the problems. But the difficult part actually is after you build your first systems, which is basically maintaining and making sure that you are updating them at a regular basis, right? We just discussed that if you don't actually do anything to your models over a period of time, they decay, which basically means you will have to, once you um, productionize and machine learning systems, you have no other choice but to keep maintaining and updating them. Apart from that, given that there are so many moving parts, what it also means is over a period of time, we'll accumulate a lot of technical debt that can accumulate in each of the systems, right? Now, this debt can be because of data dependencies, model complexity, it can be in reproducibility or monitoring, or it can be because of changes outside of the system itself. But um, there is a lot of debt which these systems uh, typically accumulate. There is a paper published by Google some time back, which a reference to which is there on the third slide of mine, which basically talks about all the various technical debts that one accumulates. So now that I have set the context in terms of the various difficulties that we have, let's visit some of the major steps uh, in the life cycle, and let's see how we can address some of the issues that we see. Data processing. We just discussed that it's very important that we spend time and effort and energy to figure out and basically correct our data collection processes, right? Now, I also understand that not always do we have the luxury of influencing the data collection process because we are probably getting this data from third party sources, which essentially means that there is a huge role that data engineers play here in ensuring that all the data in different places or different silos is made available, right? So that the researcher or data scientist can start working on it. Now, so it's very very essential that we make the data accessible and discoverable to the data scientists. Now, in today's world, especially if you are on a cloud, like you have various block storages available which typically can act as your data lake, and the other storage, which is again very common, is a typical data warehouse kind of an approach. So There are various other approaches, but a data lake or a data warehouse are two of the most common approaches. And it helps to ensure that all the data that is required, along with, when I say data, it's not just the data, along with the metadata, which includes the schemas, which includes any other information about the data itself, is available uh, to the data scientist or the researcher. Now, the other thing that happens with data when we process it is basically uh, the data keeps changing, and as and when you are actually using this particular thing in building your models, uh, you will not be able to reproduce any of your results. So let's say yesterday you were running your model on a particular set of data. Now there has been an update to it, and today you run it on the updated data. There is no way you can reproduce yesterday's results. So it's essential that uh, one should consider versioning data, and there are various tools available for the same. It's not pretty straightforward, but it's still possible, right? DVC is one of the tools. It's an open source tool. It's one of the tools which is available, but there are a few others too. Similarly, once data scientists start working on the data, whatever columns or whatever fields that they or attributes is a better word, whatever attributes that they are working on is not necessarily something they can feed directly to the models. So a very quick example that most of us can identify with is something like a categorical variable. So think of it, we have 7 days or in a week, or 12 months in a year. Now if these are represented either as strings or as numbers, now the model may not be able to take it. Typically, most models don't accept strings as an input. And if you convert them into numbers, then again they may misrepresent and assign a value or assign a weight to it, because a December is 12 just because it is higher in weight than January, which is 1. The model might misinterpret this particular variable and the value. So there is something called one hot encoding, which we do, right? So it's essential again that we keep track of all these various. This is a feature, one feature that we talked about. Similarly, there are ways in which we can handle missing values. There are ways to handle uh, other particular features where we kind of try to look at the correlations between various attributes, and maybe we reduce the dimensionality by removing attributes which are correlated, or we may actually create new attributes, right? All these are various features. Again, we go through the same issue where you kind of create these features, but then subsequently when the inputs are being given to the model, uh, they are not in the same sync as the training or feature creations, right? So this causes a problem. Now, one of the suggested approaches is to use a feature repository. There are again a few open source feature repositories available. One of them being Feast from Gojek. Gojek is an Indonesian company. They have an open source feature repository called Feast. You should consider that. Right. So essentially, the summary or the takeaway that I would have from the data processing part is be very watchful of the data that you are using, not just from the perspective of things which are beyond the scope of this particular talk, like getting the data which has proper distribution and all, but also from the perspective of versioning it so that you can actually use uh, the same data when you want to reproduce a particular model. Moving on, uh, the model exploration. So typically, the things that you would do in Model exploration, which is development itself. Like you would probably take all your features that you have created, you would go and try out various frameworks probably, or various libraries, and create multiple models and train them, right? uh, Now, the few challenges here, uh, not all your models are probably using the same framework. uh, Even if you are using the same framework, different models may differ in uh, the various other parameters, the hyperparameters and stuff, right? That's one of the challenges. The other thing is, when you are especially training, you split your data into uh, training and validation splits. Now, you also have to make sure that from a reproducibility perspective, from an understanding of the model perspective, if you want to rerun the model again, you need to run it on the same training splits and the validation splits, right? Apart from that, we all are familiar again with the model parameters that we can tweak now, and the hyperparameters that we tweak. So if we don't get this tweaking these parameters right, and if, let's say, as it happens many times, at least it happened to me multiple times, where I forgot what exactly was the parameters that I used to run on a particular run, the training run, and was never able to reproduce the same accuracies again, right? So this again is important, that one looks at versioning the code, the data, and the output model, right? Now you may not want to do the code versioning for every small iteration that you are trying to do, but you should actually look at it when you are saying this is a model that I want to train and I want to retain the output so that I can compare it against other models, or I basically want to kind of use this going down the line, right? So versioning of all of these is very necessary so that you basically can reproduce and utilize them and compare later on. Again, DBC is one of the tools that does this. There are a few others here, but DBC is one of the popular ones out there. Um, uh, Here we are still talking about our output being only one model. Now the complexity here, and even from with a version control tool, increases manifold once you are talking about dependent models. So what do I mean by dependent model? If the output of model 1 is being fed to a model 2, um, and output of model 2 is being fed to a model 3, so that's what I'm referring to as a dependent model. And you again have a lot of challenges here, because even if you improve the accuracy of a particular model, let's say I improve the accuracy of the first model, that doesn't necessarily mean that the accuracy of the second model would increase. Maybe, I mean, it would actually probably go down also. So you get the picture here of how quickly the combinations can go. Like once you have more than 2 3 models, and you want to ensure that the whole system of the cascading models works well, not just one model, right? Once you figure out which model to run, let's say the data scientists, they are happy with a particular model, saying that we are very good with this model in terms of the accuracy it gives, and in terms of various other parameters, in terms of precision and recall. Let's Now you will have to decide on how you want to serve it. Now, typically there are three modes of serving the models. One is you embed it, you kind of create the model as a package, and you embed it into your code in your application which is using it. That's one where you go ahead and you version the code and the model or since it is completely embedded as a package, is versioned along with it. The other way of serving models is as over an API. So let's say you kind of want to serve this model on a REST API or a gRPC kind of a thing. You wrap the model with the appropriate framework which serves this in this particular manner. This works in fact, this is one of the most common ways of serving the models. However, one has to be aware that this also introduces some amount of latency depending on the system that is used for serving, and so we need to be aware of that. The third is basically publishing the models as data itself, where your systems actually load, treat this model as a data at runtime, right? Um, so that's another way of serving the model, right? These are the three popular ways. Um, Now, I have also seen a few other deployments where people actually code a model. Once the model output is there, they analyze the output and they try to then implement or re-implement that in a different language where uh, essentially they are now creating a rule-based system or a pure algorithmic system and not a machine learning system. But then they do have some stringent performance criteria in terms of the response to be within a few milliseconds, right? Like less than 5 milliseconds. Now that's a very stringent performance criteria, and in such cases, you may take this model that you are given, then try to mimic the same, uh, or kind of create a rule-based and model-based combination. So there are various other complex ways, but the three that we discussed here are the most common, right? Um, the thing that you have to remember is, irrespective of which way you are serving or which way you have decided to serve your model, the most important thing here is that the contract between the model, that basically what input goes to the model, what output comes from it, from the consumer perspective should be the same. What I mean is the software which is consuming these models, um, that should maintain the same contract. In case many times, because of the first people issue that I touched upon, because there are the various teams, they don't have proper collaboration, and the friction between the teams is high. What happens is, the data scientists or researchers, they go ahead and change the model input output without actually the machine learning team or the team which is responsible for maintaining the production systems being aware of the same, which again causes a lot of heartache. So it's very important that there is a contract which is very well defined and that's adhered to. Then testing and validation. As we know, any software has to have some amount of testing validation aspects to it. Now, this is slightly challenging in case of ML as usual, because of all the various changes that are possible. But one of the things that typically we look at is validating the data itself, right? And when I say validating the data here, I'm actually talking about immediately after the data collection and subsequent analysis, right? Uh, so we typically look at validating data against a schema. I also understand that in some cases, uh, people say it's not possible to have schema and all, but I believe that's a very lazy approach to engineering. Unless you treat your data properly, unless you ensure that you have proper schemas against your data, I mean, you will not be able to build reliable systems, right? So it's very essential that you have these schemas with you, and when you are validating your data, the incoming data, both during training and also during production, right? You should validate against this schema. Apart from that, one should also look at validating the data subsequent to feature generation, uh, and at any other step where there is a the data is manipulated, right? That's basically the input data validation. Then we also look at validating the model output itself, as per what the consumers of that particular model is expecting. Right? That's one. Again, these can be automated. Um, there is another model quality. This is something that is happens. You still can have automated thresholds, so that you know when a model is basically behave is out of bounds of what your expectations are. But a lot of times between models, the model quality testing is more manual, where the researchers look at various parameters like accuracy, or area under curve, or the precision and recall. So these are some of the things that they look at. Um, it's important that one also puts in checks and balances here for productionized systems, where they kind of get alerts um, when the predictions or inferences fall out of the acceptable accuracy range, right? Another one that we should look at is bias and fairness. As I mentioned earlier, also, you might be training on a particular data set which is highly biased. So, one has to be aware of the domain that they are working in. One has to be focused on trying to figure out any inherent biases that might have creeped in because of the origin of the source, right? So think about it. If, let's say, we are doing a face recognition system in India, in South India, then we have another data set which does the same face recognition for where the data set comes from the northern part of India or the northeast part of India. Now, a single model will fail at least on one of the data sets, right? I mean, so if it were trained on South India, there is a high chance it might fail on the North Indian or the Northeastern data sets. So it's important that the researchers actually kind of pay attention to the inherent biases that can creep in, and build their um, systems for that. Now, the other complexity that happens with data is data changes over time. So it's very hard to kind of assess your models and their behavior over a period of time. So if you kind of keep the data set the same for a long period, then it leads to overfitting, and it may not actually be representative of what you want the system to do, right? Next, we discuss deployment. You have different ways of deploying, one of them being multiple models. What do I mean by multiple models? So let's take an example, right? A Swiggy has to predict how long it will take to deliver an order, or how long a restaurant will take to deliver an order. Now, they have different models for different geographies, right? One for Kormangla, one for Indranagar, and they serve in probably some 1,000 or 2,000 odd zip codes, pin codes. So they would have probably different models for each of them, and not just for each location, but also based on the time, like different models for lunch and different models for dinner. Now, this is something that you may not want to. All this complexity is something you wouldn't want to expose to your end consumer systems. So, what would probably happen is you would abstract it away with an API, and all these decisions are taken based on the inputs to the model by the API which abstracts this away. So this is one example of multiple models. There is another one which we slightly touched upon earlier in terms of the dependent models, which basically is you have models where you take the same example, right, for Swiggy, to predict how long it will take to deliver to for a restaurant to deliver. They will have to predict how long it will take the restaurant to prepare the meals, how long it will take the restaurant to package it, how long it will take for the delivery boy to pick it up and come back and drop it at the customer address, right? So now, from a training perspective, all these are maybe independent or maybe cascading, but from from a serving perspective in the production, the output is utilizes basically all of these the outputs of all these models, right? So that can be another example. Another way of deploying is shadowing. This is again a common method which is used when people try to uh, validate how their models are performing against an existing model in production, right? So what actually happens here in shadowing, you have a parallel system where all the input are sent to both the production model and the new model, which is pending validation, right? So once the outputs go there, then you once you get the output from it, you then compare it against the production system, and based on that take a decision on the rollout. So then you have something called split serving, where you typically do A/B tests. So in the earlier one, it was shadowing, where all the 100% of the traffic was going to the new model also, as well as the old model. Whereas in the split serving, you typically do an A/B test kind of a scenario, right? Um, Apart from that, you also in some situations where you typically use reinforcement learning kind of models, where the systems are learning as at real time, right, as and when the traffic is coming in. Now you would have noticed that all of these four different kinds, and there would definitely be a few others, but these are the major things that are common across deployments, right? They require different approaches to the infrastructure underlying. So that's something to keep in mind. One challenge with online learning models, which is um, they completely throw uh, all your processes of versioning the data, versioning the models, and version both models and data into a spin, right? Because things change dynamically at real time. So yeah, that's something that needs to be kept in mind. Uh, the final one, but not the least, is monitoring and observability. This is pretty important because, um, unlike software systems, which I mentioned earlier in the day, in typical software systems, you more or less care about whether the system is available, whether it is functioning as per your parameters of performance, and so on and so forth, right? You actually, in many situations, you in production, you are not too much worried about what is the input and output. uh, uh, you would be worried about the performance characteristics, as I reiterating again, but not necessarily the input out parameters, right? And you would have a system in place to handle exceptions, again, which you would be logging and monitoring. But when it comes to machine learning, you have multiple other things that you would worry about. One of them being what exactly is the data that is being fed to the model. This helps you kind of check how much is the skew between the real world data which your model is seeing out there to what you have trained, right? So it's a very important parameter, because as if the skew increases, that basically means you are going to have very bad predictions, which may impact um, the complete system, right? The other thing is also you would definitely want to log the outputs, and so you just don't want to log the model output itself, but you would also want to log what the consumer who consumed this output gave out, right? So you would also want to look at both of those. What is the model output itself, and what is the decision made by the consumer who is using this model, right? Um, Apart from that, the next thing that you would also want to consider about is the user actions. So an example is you have an e-commerce website where you have a recommendation for purchases. You would not just be uh, keen to understand what recommendations the system gave, which is the output of the particular model, but also what is the final outcome in terms of whether the particular user has performed an action of buying or interacting with that particular recommendation, right? Which is also critical, because you are not just trying to, the whole idea of recommendation model is to probably improve the user engagement or improve the cart value. Now, if that is not happening, you may have the best of recommendations, but if it's not meeting your goal, it's not useful. Um, then we have things around fairness. You again, you would want to log all the data so that you can look at uh, the inherent biases which are there in your data, right? Which you are feeding to the model also. The other reason why you want monitoring is basically to interpret the outputs. So you basically log all the things like the coefficients, uh, etc., so that you can basically investigate the model output if something is wrong or not according to what you expect, right? A lot of times, a lot of people use the ELK stack here, which is Elasticsearch, Logstash, and Kibana, or Elasticsearch, Fluentd, and Kibana. So both these stacks are used. Um, yeah. Another challenge that comes up is on edge systems, which is basically your mobile phones or your IoT sensors with some capabilities of machine learning and all. Um, it becomes much more critical in terms of the monitoring, because um, because you can't update your edge systems so often and so frequently as you can possibly your server-side based systems, which basically means that there is a lot of divergence that might happen with the actual in the behavior of the model, right? So that's primarily around model monitoring observability. Um, my last slide. On the whole, the takeaway is we should accept that machine learning systems are hard to maintain. As I said earlier, and I reiterate that again, in today's world, it's very easy to create a machine learning system or machine learning model and deploy that. But the actual work and actual complexity starts the moment you deploy your first model, right? Because the clock is ticking, and if you don't do anything about it, it becomes stale, and it might actually um, give a negative outcome to what you were expecting. So please, first thing, accept that machine learning models require some amount of maintenance, and they require a different process which is different from traditional software. From an approach, many a times uh, most data scientists may not necessarily follow the same principles of software engineering in terms of version control, in terms of in terms of automating tests, automating deployments, and all. But it's strongly recommended that people take a software engineering approach to this. Uh, Also, all your processes, whether it is manual, highly recommended to make them automated. But whether it is manual or automated, ensure that they are reproducible and auditable. Because if something goes wrong, there is no way you would know why it happened or what it happened, even if you have all of the reproducibility and auditability. And now, if you don't have that, it's completely like magic, right? I mean, version your data, version your models, version your code. That's the other one. And then think of this whole thing as a platform, and not a piecemeal solution where a data engineering is doing something, data scientists are doing something, or the ML engineers are doing something else. In your organization, think of this as a platform which everybody uses and is dependent on it, and that's the only way to may ensure that one, everybody uses it and also complies to it. Yeah, these are the primarily what I wanted to share with you guys today. I am done with my slides. Any questions? Any any questions? I'll be happy to take. Yes, Preetham. Okay. Preetham has a question. Sorry, I think it is Suprita Bhaskar. She has a question, which is, could you brief out more on versioning data? Yeah, sure. So what happens is, let's say we are working on the orders data, right? And we take the month of September 1st to 30th of September, that 1 month. Uh, Day one, we take 1 month data, and we are basically training our models on top of it. Now, so by just stating that I am taking 1 month of data from September 1st to 30th September, I have kind of bracketed saying this data is version for this, right? Now, how do the tools do? Tools follow a similar approach. What they do is, as I said, DVC. So you have to call a couple of commands to version your data, but the process would be something like this, right? You run your models on a particular set of data, and once you are happy with what it is, you commit both the data, the model, which is the output, and the code itself, right? And when you do that, underlying DBC utilizes Git. So what happens is, uh, it basically takes all the data, stores it in a blob storage like S3, or E2E has their own blob storage, so it stores it on the blob storage, and generates a hash. It commits this hash, which is generated for the data. It commits the code and the model into Git, so that next time when you want to kind of use that, you have all this available with you. Does that explain help you? If you need more clarity on this, please put a question in Q&A. I'll move on to next question from Naveen. He's asking, can you explain how online learning is done? How is it different from online inference? So when I said online learning, it primarily refers to reinforcement learning kind of a thing, which is a branch of unsupervised learning, where you basically deploy your unsupervised models, and as and when the data comes in, it basically what do you call generates the inference, right? I am not a data scientist, so I can't get into deep in-depth knowledge of how a unsupervised learning model works, but this is primarily what happens in the online learning example that I gave, or the which is for the unsupervised real-time learning, right? How is it different from online inference? In my definition, online inference, I take it as something where I'm doing uh, in real-time inference. Right, the model was created earlier, but I infer at that particular like these are real-time systems, maybe a order prediction system, or maybe a recommender system. So I look at these as online inference systems. Preetham, if you have a question, maybe you can ask, or you can type in Q&A.